SwayamPrabha. Digital India. Educated India.
So, we have been discussing about spinodal decomposition, and in the last lecture I told you that spinodal decomposition is basically leads to separation of fluctuations or growth of fluctuations which are present in the microstructure. Now, as you know, if we consider a phase diagram and which has a miscibility gap, and then if we quench an alloy within the miscibility gap, it is very clear that composition fluctuations will grow because of the reduction of the free energies. Now, these composition fluctuations which are there at the beginning when the alloy was quenched within the miscibility gap is supposed to grow as a function of diffusion coefficient, temperature, and how it depends on these parameters, that is what is we are going to discuss today. So, in order to know that the composition fluctuations has a particular wavelength which grows and becomes part of the decomposed microstructure, we should know how the free energies of these systems are determined. So, I will first go to the board and tell you how these composition fluctuations actually grow. Let us consider a simple situation. Okay. Let us suppose if I have a phase diagram which shows a miscibility gap like this, and a quench an alloy from temperature T1 to T2, which is a composition of X0. Now, it is very evident that as you quench this alloy from high temperature, which has a single phase solution alpha, this is going to decompose into two different phases with compositional fluctuations. Okay, now, as we have seen, there is a chemical spinodal within which this decomposition happens, because the free energy, double derivative of free energy with respect to composition is less than or equal to 0. That means these points actually tells you the curvature of the free energy curves as a function of composition variable x b is negative within this. So, now that means that these are the 2 points x1 and x2 at which these compositions, these alloy will decompose without any need of any nucleation or growth. That is what is called spinodal decomposition. So, if I take a simple, if I draw a simple set of composition profiles like these, let us suppose this is xp, okay, and if I plot this xp as a function of distance x, okay, small x. So, what will happen initially? Let us suppose this is x 0 and this is x 1, this is x 2. Okay, initially whatever homogeneous solution is present, as the time goes on, this will start decomposing into two different parts. So, if I draw again x 0, x 2, x 1, so these alloy will start decomposing into two phases. Let us draw it in bigger way. one with a composition of x1, other one a composition of x2, and that is what is basically known as compositional growth of the composition fluctuation. So, as you clearly see, there is a particular wavelength lambda we can assume of this compositional fluctuation. Now, how we can actually determine what is the minimum lambda possible, because as the lambda decreases, as you see here, as the lambda decreases, the wavelength is basically will lead to increase in the interfacial energy of the system. So, therefore, this will be a optimum choice of lambda by which this decomposition form and composition of alloy x0 to x1 and x2 can happen. Okay, finally, actually at the end this will be like this. X2, x0, x1. So, if I draw, this is okay. So, this part, top part is basically for the alloy, the region which has x2, and the bottom part is basically region with x1. Okay, that is how things will happen. Now, we are asking a question that how we can determine lambda. To know that, we should know how the free energy of these alloys will change or will be evolved. So, we need to consider two important aspects. One, obviously we actually need to consider three important aspects. So, free energy of the system needs to be calculated. How we calculate free energy of the system? It depends on three things. One, obviously, is the chemical part of the free energy, chemical part. Second one is the interfacial energy part, which is also known as gradient energy in this system, interfacial energy. So, let me write chemical free energy, interfacial energy or gradient energy, and third one is strain. So, we will discuss one by one and then we will develop the full equation. What is the chemical free energy system? It is very clear. If we start with an alloy x0, the initial fluctuation will be x0 plus delta x and x0 minus delta x, right. That is how the compositional fluctuations will grow. Initially there will be no fluctuations, and at the as soon as the sufficient energy is available for the diffusion to happen, this will decompose into two phases with composition x0 plus delta x, x0 minus delta x. Now, it is very easy. If I have an alloy, if I have a system with phase with the composition x0 plus delta x and x0 minus delta x, the chemical free energy delta Gc is basically half of dG by whole square. That is how it will depend on. So, therefore, if I know the free energy is function of x, x is the composition variable here, and if we know the compositional differences which by which these fluctuations are growing, then this is the chemical free energy part of the system. This can be derived very easily. It is there in the books also, so I am not going detail. Obviously, this depends on the curvature of the free energy curve. Why? Because free energy curve, as you know, is look like this. Okay. So, there are two inflection points here where the curvature is 0. So, this is my G versus XP curve. This is I have already discussed in the first lecture. So, what you need to know is that the functional, because of double derivative of G as it is depends on X mostly. So, that we need to know, and then if we know the compositional fluctuation we can determine the chemical P energy part. Now, what is the interfacial P energy part? Well, as you know, at the beginning when the compositional fluctuation is very small, that means you have regions which is reach in some element by very small amount, lean in some element by very small amount, okay, finally dispersed. So, what will happen? There are going to be interfacial energies because of that. What is the origin of that? It is very simple. This system is basically cluster based system. Why? As you know, if I have a homogeneous alloy composition X0, as it is quenched at temperature T2 from T1, it is decomposing into two phases with a composition X2, X1 and X2, right. So, X1 is A rich, X2 is B rich as compared to X0. So, that means what? The regions which is A rich has more A clusters, regions which are B rich has more B clusters. As the time goes on, this decomposition will happen more and more, as you clearly see, this decomposition will happen more and more, and finally the region will be A rich and B rich, okay. As you know, this energy curve will look like this, okay, region will be A rich and B rich. So, this system is basically cluster type, that means you have regions of A cluster, regions of B clusters, that is what is that spinodal decomposition looks like. So, now question is this, if this is what is the situations, the interfacial energy is basically because of this dissimilar atoms present in the systems. Even at the beginning when the decomposition is happening with X0 plus delta X, X0 minus delta X, these regions are finally dispersed, still there will be dissimilar clustering of dissimilar atoms or basically presence of dissimilar bonds which will lead to interfacial energy. And as the system grows, they are becoming more and more A and B rich. So, therefore, these regions are actually the regions, this is suppose this is an interfacial boundary where you have B rich region and A rich regions sitting side by side, and this leads to bonding between dissimilar atoms, and these dissimilar atom bondings will be lead to higher interfacial energy. Why? Because system does not like to be staying as a dissimilar atoms. This is different from the random solutions where system will have more number of dissimilar bonds than the similar bonds. Here system will like to stay in such a way that clusters of A rich and B rich atoms are present in the alloy. So, whenever there is interface between A and B rich, there will be dissimilar bonds, and dissimilar bonds will lead to interfacial energy. How to calculate that in this one? Obviously, this interfacial energy depends upon the gradient of the compositional gradient. Now, let us assume that the compositional gradient, compositional profile, although this is what I have drawn, it looks like this exactly. So, it looks like sinusoidal type, okay. This is what is that, this also looks like that, okay. It goes up, goes down, goes up, goes down like that. So, if I have a wavelength of the compositional fluctuation which is sinusoidal type of lambda and amplitude of delta x, this is the amplitude of this wavelength delta x as you see here, then it is very clear that compositional gradient is basically nothing but delta x by lambda. This is the compositional gradient, correct. So, if I have such a kind of compositional gradient, the energy of the system is basically an interfacial system is basically a constant times delta x by lambda whole square. Okay. Why? That is because this is you know this is compositional, that means this is atom percent and this is the distance lambda. So, it is atom percent by distance. So, in order to make it having units of the Phi energy, we have to multiply with the constant k. K is basically gradient energy constant, okay. So, therefore, this energy also known as gradient energy because of this compositional gradient present in the system, right. So, we have seen that the chemical Phi energy is like that, compositional gradient leading to interfacial energy is like this. Now, let us also calculate the strain energy. First of all, let us understand why the strain energy will at all be exist. Well, if the regions which are compositionally different, like region which has composition x0 plus delta x, region composition with x0 minus delta x, their lattice parameters are different, okay, then this will lead to strain energy. Obviously, because if I have a region with a high lattice parameter sitting next to the region with a low lattice parameter, there will be strain, at least elastic strains will be present, and this strain will lead to energetic effects. How do we calculate that? Well, that can be also calculated similar way. Let me just erase this part. That can also be calculated in the same way. It is very simple that strain energy Gs is proportional to elastic constant E multiplied by delta square. Why? This is Young's modulus or whatever you say, okay, and delta is nothing but the basically the misfit. Misfit is what? If I have a region with a lattice parameter A1 and region with a lattice parameter A2, so A1 minus A2 divided by A1 is what is known as misfit, okay. One can also define other way, A2 minus A1 by A2, that also possible. So this is what is known as a misfit. Now if I know the misfit and if I know the elastic constant, okay, then we can calculate the Gs. Obviously the delta depends on the compositional variations. Let me just see, delta will depends on compositional variations and it depends on compositional variation in the same way. So this is the misfit, I have told you. Basically delta is can be written like this, delta x by A multiplied by d A by dx, where A is the lattice constant of the solution, okay, random solution. So if I have a compositional difference of delta x and lattice parameter A, this multiplied by this derivative will give you basically delta. Now we can actually write down delta Gs much simpler way. What is that? Eta square delta x square multiplied by E, because this is proportionality constant. So now I am writing you, giving you the full formula. So you can see here this is eta square delta x square E prime, remember this is E prime not E, and Vm. Let me just define each of these things. So delta x is obviously compositional fluctuations as you see here. So what is eta? Eta is one like this, eta is 1 by A multiplied by dA by dx. Basically we convert delta to eta and this is the way it is converted, that is why delta x square comes here. Delta x here, so 1 by A dx by dA can be written as, so basically this is nothing but delta x multiplied by eta, right. So that is why if I have to calculate delta square, this become eta square and delta x square, and E prime is basically E divided by 1 minus nu, where nu is the Poisson ratio and Vm is the molar volume. So now we have all the things together. Now we have the expression for chemical P energy, expression for gradient energy and expression for the strain energy. So let us now put them together, okay. I will erase some part of the things so that I can explain you. So let us put them together. So total energy of the system G can be written as very easily, can be written as like this. Remember this energy is minus, why? Chemical P energy is always minus, we do not write it but it is always negative, because that is what is driving the whole system for transformation, right. On the other hand, these P energies are positive terms, the gradient energy or the interface energy and the strain energy, that is the convention we always use. So therefore I can write down these as like this minus this one, that term, plus, okay, plus 2k by lambda square, remember 2k by lambda square. Remember what we are doing, we are taking x delta x square out from the system, basically, plus twice eta square E prime Vm, okay, that is what am I saying, into delta x square by 2, okay, that half which is present here I have taken out there. So that means what, delta S is basically half of delta x square into this term, and then the gamma is k by lambda square delta x square, and Gs is basically eta square E Vms delta x square. So we get the whole expression of the phi energy. Now please remember that this is the expression of the phi energy. Now if we want this solution x at this composition I have shown you there, erase that, to decompose or to become unstable, the condition is very simple, delta G must be greater than 0. If delta G is less than 0, then it is a stable solution, right. For random solution, when delta G becomes less than 0, that is a stable one. When delta G is equal to 0, that means it is an equilibrium situation. When delta G becomes more than 0, then it is a metastable situation. That means the solution will decompose very easily into something. So if that is the case, what do I get? I get the condition for decomposition. Obviously delta x can never become 0, right. Delta x is the compositional fluctuation which is growing as a function of time. So this term must be less than or equal to 0. So that is why this will be equal to, sorry, this will be greater than, the condition for that is 2k lambda square plus 2 eta square okay. So that is the condition for decomposition. This must be satisfied in a spiral decomposition, this must be satisfied for it to be decomposing into this kind of compositionally rich and compositionally lean regions of particular component A or B. Please remember that how this is derived, because this is very important, because this particular formalism is used in all kinds of simulation softwares which are basically used to calculate the microstructure or basically generate the microstructure. Now it is very simple, now because once we get the equation, now it is very simple how to calculate lambda. Okay, so therefore the limit is what? Limit of lambda is nothing but infinity. Obviously once lambda becomes infinity, this term goes to 0. That means there is no gradient energy. Gradient energy is because of these wavelengths. So we can write down at the limit of lambda minus delta G square is equal to, or rather let us write minus 2 eta square E. This is at the limit of lambda. So that means I can have the maximum lambda possible under this condition. I can never have lambda more than these, okay, that is very simple. Similarly, I can have minimum lambda when this is equal to 0. So minimum lambda will happen when all the chemical phi energy part is consumed in creating gradient energy and strain energy. So lambda must be within these two ranges, maximum, minimum. It cannot be more than that or less than that. That is very clear. So once you consume the whole chemical phi energy, you create a minimum lambda, and once you have very high lambda, there is no interruption energy, obviously, because lambda becomes infinity, then 1 by lambda square becomes 0. So these are the two regimes of the compositional fluctuations possible, remember that. So I can write down that this condition is correspond to another kind of a spin-order which is known as a coherent spin-order. You have seen chemical spin-order, coherent spin-order. Or we can say coherent miscibility gap. Okay. So this miscibility gap, which I will show you in the next lecture, lies within the chemical spin order, because this corresponds to lambda infinity. When you have very large lambda, you have a coherent spin order. That means the regions are actually completely coherent. That is why it is called a coherent spin order. Okay, so but the limit of lambda, so therefore line on the phase diagram which satisfy this condition is actually defined as a coherent spin order. Remember, the chemical spin order actually define chemical spin order. The chemical spin order is basically first chemical thing actually depends on this condition, which I have shared again and again and shown you that. So this is different. Here this condition is different. Okay, this basically relates the chemical part of the free energy with the strain energy terms. That is why it is called as coherent spin order. Okay, so now the last thing which is important is that, so therefore wavelength of compositional fluctuations or modulation developing inside a coherent spin order must satisfy the condition like this. Okay, wavelength of let me remove all these things, compositional fluctuations developing within the chemical spin order must satisfy this condition. How do you obtain that? Very simple. Okay, you make this basically coming from this equation, that is what it is. So if I simply take this equation, let me write it that, so twice k, there's some mistake looks like, okay, that does not matter. So you can this one minus, we can do that, this all multiplied by minus, it become plus, this become minus, this become minus. So twice minus twice k by lambda square is equal to del g square by del x square plus twice eta square e prime Vm. So you can clearly say that from this we can get lambda square will become minus twice k divided by this term. Okay. So that is how actually we can obtain the equation of lambda or minimum value of lambda like this. So that must be satisfied. So lambda must be greater than that, otherwise you cannot have a compositional fluctuations stabilized. Okay, so that is the crux of this lecture today. So therefore, what we discussed? We discussed how to calculate the free energies of the system. So we discussed how to calculate chemical part of free energy, the gradient energy term, which is basically because of the compositional fluctuation we are developing a interfacial energy, and finally because of this misfit, lattice parameter misfit of the compositionally decomposed regions, we have strain energy. Once you put all these things together, we get the full free energy expression, and that we can then mathematically analyze and find out the different conditions of the transformations. So we can actually get ranges of lambda from infinity to finite value or minimum and maximum minimum values and analyze that. So that is the basically important part of these spin order decomposition, which is distinctly different from others. Remember, this is a diffusional transformations. So within the chemical spin order, the interdiffusion coefficient is less than is basically negative. Interdiffusion coefficient means the diffusion coefficient from one region to other region, from a compositional rich region to the compositional lean regions, the diffusion coefficient is basically negative. That is why this transformation happens so fast. The diffusion is basically uphill diffusion. Diffusion is not a downhill diffusion, and that we discussed many times in lectures, in diffusion course also, diffusion part also, and in this lecture also. So the next lecture, at the beginning of next lecture, basically I will show you some of the microstructure and some of these different lines like chemical spinodal, covalent spinodal, and again and then conclude the whole thing. So, next important topic which I am going to discuss basically transformations which are basically not important so much normally we think, but they are important. Few of them are actually cellular precipitation, which I am going to discuss couple of lectures. Then I will also discuss some of the phase transformation in the ceramic system, mostly the toughening transformations, and that is how you will wind up the course.